Hey everyone, I'm Dr. Bob, and in this video I'm going to talk a little bit about Unity's rendering pipeline, which also involves materials, textures, shaders, meshes, and whatnot. Let's get to it. So as you're designing a game, you're probably going to build a scene of 3D objects, well, if it's a 3D game at least, and then you're going to take that scene and convert it to a flat 2D image that you actually see on screen. That process is called the rendering pipeline. And Unity actually has a number of options for that. There is a built-in render, which is a general purpose pipeline. But you can't make too many customizations to it, or at least not easily. There's the universal render pipeline, or the URP, which is the one that we'll be using in this series. And that's a scriptable pipeline that you can easily customize. It's focused on optimization. So for mobile games, it's really useful, or for games that don't really require high-end computers. Then there's a high definition render pipeline, or the HDRP, which is a very scriptable pipeline as well, but it's mostly for high fidelity graphics. So this is for PlayStations or for people with high-end computers. If your game is really about making it look as beautiful as possible, that's probably what you would want to choose. And you can work on your own render pipeline using Unity's scriptable render pipeline API. So anyways, for this class, as I've already mentioned, we'll use URP unless otherwise indicated. And the rendering pipeline for Unity consists out of three things. First, there's culling, then there's the actual rendering, and then there's post-processing. And those are going to be the three topics that I'm going to address in this video. So let's start with culling. Culling basically determines what is going to be rendered, what is going to be drawn on screen, if you will, and what is not going to be rendered. And this is mostly something that you do for optimization, because all the rendering, all the drawing, every time your computer is going to have to calculate what something will look like in this 2D space, it all just takes processing power. So to make sure that our games are as optimized as possible, we're first going to look at like, well, which of these three objects in the scene do we actually want to render, and which ones do we not want to render? And that process is actually called culling. And there are some different methods of doing that. For instance, there's one called frustum culling, which is basically looking at where the player is looking, what is going to be in view of the player camera, which is not going to be in view, and using that information to cull. There is culling called backface culling, which is you're not drawing the back of a certain 3D object. And then there's occlusion culling, which is not rendering objects that are being pushed out of view by other objects because they're behind them for example. So let's take a look at a couple of examples of that. So here we can see a visualization of the frustum, and it's not frustrum. There's no second R in there. It's frustum. It's a often misspelled word. So, and I'll probably misspell it in a bit anyways, but the frustum is basically a word that means a pyramid where the top is cut off of. And if we have a pinhole camera, like what you see on the slide here right now, we would have a pyramid. But for rendering purposes, we make it a little bit easier on ourselves. Instead of just having a small point, we're kind of imagining that our screen is going to be in this area. And this is our 3D scene that we actually have. So we draw this flat pyramid and we cut the top off of it to try to figure out what image we need to draw on screen. And this has a near plane and a far plane, as you can see. So that's the general principle behind frustum culling. Frustum, not frustrum. Let's have another illustration of that. So here we don't really see the frustum as the pyramid with the top cut off, but it's the same principle again. And you can see there's a bunch of objects in this 3D scene. So what is going to be culled and what's not going to be culled? Well, if we're doing frustum culling, everything that is out of view is not something that we want to render on screen. We don't want to spend any processing power to calculate the lighting and to calculate what that object will look like in that 2D space. So applying that will make all those objects basically disappear. Now in this case, this object is kind of half and half. So for the sake of this image, it's still being calculated and rendered on screen. So that's an example of frustum culling. Now, if we look at the occlusion culling that we discussed earlier, then we're also going to look at which objects are within the frustum, but are not in view of that camera. So in this case, the cone that we have here, the sphere that we have here, they're all obscured by other objects. So we're also not going to calculate them. We're not going to render them on screen. So that's an example of the frustum culling, and that's an example of the occlusion culling. And here's another visual to illustrate a little bit further. And this also includes what is called backface culling, which is we are only going to draw parts of the object that are actually in view. So why would we spend time rendering the back here if that's never going to be seen by the player? So here we can see all three of those examples neatly into one image. Now, you might be thinking, haven't I heard that technique before as clipping? Or rather, when clipping is referred to, it's typically referred to in errors that you see on screen, like what you're seeing here. This sort should be visible if it's there, but it's, there's part of the back of the character that has the sword go through it, which looks off. It's not what it's supposed to be. I mean, there needs to be a way for the sword to be attached to the player, I guess, but in most RPG games, it's just kind of floating there and just magnetically attached to the player. So usually when this type of issue happens, if you can call it an issue, gamers refer to clipping. So it's clipping and culling. How do those terms relate to it? Well, culling is usually used when we are referring to the full object. As you saw in that image earlier, the one, the blue circular object that was to the right of the image, part of it was still there because part of it was actually in view. So we're talking there because we're looking at an object if the entire object is going to be in there or if the object is not going to be in there. When we're referring to clipping, usually that term is used to remove certain parts or stop rendering, stop drawing certain parts of the object that are not going to be visible. So if an object is only partially visible, we're referring to clipping. Now, there is no single definition to either of them. This is very confusing, and a lot of the times it comes down to the algorithms that are being used, whether the person who developed the algorithm is referring to it as a culling method or a clipping method. But in general, when we're talking about entire objects, it's culling. When we're talking about partial objects, it's clipping. So when we were looking at the earlier slide here with the backface culling, you could say that that's actually clipping because that is a part of the object instead of the entire object that is not being drawn. So that's one thing. Another thing there is most of the times when clipping is used, especially when gamers refer to it, they are actually talking about collision issues rather than actual culling techniques. Take for instance the image from NBA 2K that we have here, or actually that sword as well. It's a collision issue here. The hand of this player here is going through, I think it's Dwayne Wade's face, and that's not supposed to happen. This has nothing to do with performance or, making sure that we are optimizing rendering here. That arm should just not be here. It's a collision problem, probably caused by the animation, because NBA 2K uses scanned animations that are somewhat procedural, I think, but who knows? I'm not a developer on NBA 2K, but in any case, this is not really about culling or clipping in that regard, but clipping is often used to describe this process as well. So that's good to keep in mind as well. When we're talking about clipping, oftentimes it refers to actual collision issues rather than culling where we're trying to optimize the way our game is rendered. Finally, for clipping, there are many ways to do it, but usually the algorithms will split an object in both its visible part and its non-visible part. So you're turning one object into two objects, and you're not rendering the non-visible part while you are rendering the visible part. So that's culling and that's clipping. Now, once we have figured out what we want to render, what we want to draw on screen, what we want to calculate the lighting for, and the vertices and how everything is positioned within the 3D space, we get to the rendering, and that's going to be the next step that I'm going to be talking about. So as I mentioned earlier, rendering refers to drawing the 3D objects on the scene. So it starts with the 3D object itself, which is the mesh. So the mesh is the definition of the shape of a 3D object. It is all the information that make up the 3D object as it's going to be drawn in a 3D space. And it has a number of elements: vertices, edges, and faces. I'll demonstrate that by opening a 3D model in Blender. So here you can see the typical Blender monkey that's often used for tutorials. And yeah, I mean, it's a standard model that comes with the software. So if you have Blender on your computer, you can add your own monkey by typing Shift and A at the same time to add a new mesh. And you can go to mesh and then click on monkey to add one. I've already have one, so I'm not going to make another one. And yeah, I'm moving around a little bit, having a look, but as you can see, this is a 3D object. And if I would want to edit this, I can click on it and press the Tab key. And with that, we will see what is actually going on to render this on screen, because obviously since it's being drawn, it's being rendered. So there are vertices, and the vertices are all these points that are connecting the lines to make up what we perceive as the face of a monkey. So pretty fun. You can click on them, and you can actually change between vertices. So vertex, that's this one here. Lines, that's the second one. So you have lines that are between the vertices, and then the faces, which are the filled up spaces in between the lines. So you can switch in between those. So if I select this one, I can select the lines, but now I can no longer select the vertices because that's how Blender works. And if I click on this one, I can now select faces. So, and if you don't have a face, you have an empty space. So let's say I select this face and click on delete and delete the face, you'll see I can look inside the skull of the monkey. Cool, right? All right. So anyways, this is a mesh, and a mesh consists out of vertices, lines, faces. And yeah, I mean, you can move these around. Like if I select the vertices or a vertex, I can click on it, I can press the G button, and I can start moving it around, and I can change the way my mesh ends up looking. Now he has kind of a cool haircut. All right, so I'm going to Control Z this back to where it used to be. The other thing that I wanted to point out about these meshes is that we typically express them in either tris or tris and quads. So as you can see here, I'm going to select the faces again. Every face consists out of 4 vertices. So a certain amount of vertices, whether it's 3, 4, 5, 6, 7. I mean, if you have 2, you only have a line, obviously. But those are polygons, and a polygon that consists out of 3 vertices is called a tris or a tris. I call them tris. And one that consists out of 4 vertices is called a quad. So these are all quads. The reason why this is built out of quads is that for the human brain, it's a lot easier to visualize a 3D object using quads. And that's why it's built like that. However, a computer, well, and for math in general, it's a lot easier to work with triangles. So a lot of the times when you download a 3D model from the internet, you're not going to have quads unless you get a source file. Most of the time, it's already going to be converted into triangular polygons, which is actually pretty easy to show in Blender. If you click on face and you click on triangulate faces, you'll see how everything is triangulated. And as soon as you export this to an FBX, it will remove the vertices. It'll start triangulating everything automatically. Now, thankfully, you can also, if you want to make changes to it, you can select everything, go to face, and then go to tris to quads, and it will revert it back to quads. Now, that works really well for this monkey head, but for most 3D models you'll get from the internet, results will vary quite a bit, and it's not going to be super helpful. For instance, as you can see here, there are still trisses in here. So, you know, you can go to face, and then you can, what is it again? There is an option here to welt them. No, that's not the right one, but you can, there's options in the 3D modeling software that you can use to turn a tris and a quad manually, but it's a lot of work to do that. Anyways, the point being is, what I want you to know from this is that there are tris, that there are quads, that there are polygons, and that there are lines, edges, rather, faces, and vertices that make up a 3D model, that make up a mesh. And that's pretty much what it comes down to. The final thing that you want to be aware of when it comes to this is that the more lines you have, the more polygons you have, the more your computer is going to have to calculate. So if this is a very complicated model, which the monkey is not, it's going to take up more processing power. So you want to avoid having a lot of these. You want to have as few as possible while still having a nice detailed figure. So for say a character in a AAA game, like 10,000 polygons is reasonable, but for a calculator or an object that the player won't, I don't know why I said calculator, but any object that the player won't interact with in the video game that much, or that will never be close to screen, it could be a lot less polygons than that. Like maybe you're shooting for 100 or 300 or so. So anyways, that's kind of what I want you to take away from this. And if you want to use Blender to figure out how many polygons a model that you downloaded from the internet actually has, you can click on your viewport overlays and then click on statistics, and it'll tell you. So right now, well, it'll actually tell you what you select as well. So now this monkey head, I think, yeah, the monkey head, I think it's called Cezanne, is having 507 vertices, so the points, 1,000 edges, and 600 faces, and in total it would be about 967 triangles or tris. So that's not too bad. That's really not that demanding. So anyways, let's leave Blender for now and have a look at how we can add some color to a model like this. So adding color to your mesh is done by means of a texture. Now, textures can do a lot more than just adding color to a mesh, as we will see in a minute. But in general, a texture is a bitmap image that you're gonna spread out across your mesh's surface. And the information that's contained in that image, which oftentimes is color, will be used then to tell your game engine to perhaps make a certain part of the mesh a certain color, or to maybe add small details to the mesh, or to impact how reflective of light that mesh is going to be in a certain spot. Like maybe you want it to be very glossy or something like that. So let's have a look at a couple of examples that show you what textures can do for your meshes. So the first one is the albedo map, and an albedo map is commonly used to provide color. So if you remember that monkey that we had earlier, Cezanne, well, here she's again, but this time there's color on it. And we can see what that looks like when the texture map, which we can see on the right here with the UV inside of it. So the UV is basically when you unwrap your mesh, when you are going to take all the parts of the mesh and project them onto a flat 2D image so that you can, for instance, say, this area here, let's say for the eyeball, corresponds to these areas down here. They're stretched out a little bit so that you can put more information in it. But as soon as this albedo texture image is applied to this, it's going to get stretched and wrapped all around the 3D mesh here. So here we can see all the colors, and here we can see how they are actually applied when we wrap around them. And that's what an albedo does. It will usually be used to provide color in certain spots so that you get a colored mesh, so that you can have skin on a body, or that you can have blue eyes, or, you know, whatever color you need in whatever spot you want it for your mesh. So that's an albedo, but like I said, we can do a lot of other stuff with it as well. For instance, we can add detail to a texture map. This is done by using a normal map, and on the left here we are seeing what a wall would look like with just an albedo, with just color on it. And yeah, sure, with color we can draw bricks and everything, but it's still looking very, very flat. Now, don't mind the specular light on here that much. It's just light that's coming in from a light source that is pointed to that specific spot of the mesh. But in general, this could literally just be one polygon with 4 points. That's not the case right now because this has rounded corners for artistic purposes. But in general, this doesn't have to have a lot of detail, and there's, for that reason, also not a lot of depth to it. However, when we add a normal map, we can add small details to our 3D mesh, as you can see here. And the right side seems to have a lot more detail. It seems like you can rub your hand over that wall and you would actually feel different indentations and bumps all over that surface. So that is done by providing a normal map that the game engine can then use to determine how light should bounce off of this and give you the illusion of there being a lot of tiny detail. Now, that's actually a really good way to make sure that you don't have to calculate too many of these polygons. Because like I said, this could literally just be one polygon, but if you want to make this just by adjusting the mesh, you're going to need a whole lot of polygons to get that kind of a detail in there, to just move the mesh around a lot. So with a normal map, you can just have one polygon and get this kind of detail. And that looks like this. So a normal map typically has a neutral value of this purple bluish, depending on how you perceive this color, because it's a color that could have many different terms, I guess, but it's purpley bluish and it has some red and some green in there. The red will determine areas that are going to be raised a little bit, and as you can see here, let's say that this is a top-down view of 3 edges, well, 3 faces really, top down, and we want to have some detail there through the normal map. We could have a normal map that puts these values on these pixels, and in this area it's turning a little bit more red, so we are going to raise that surface a little bit and add some detail. So that's basically what a normal map does, and that's what a normal map looks like. And again, This is just a 2D image. This is the entire normal map that you can just apply to a mesh in the same way that you would apply this image to this mesh to add color to it, to add that kind of detail to it. So that's a normal map. And then we have a couple of other maps that are used for reflectivity and controlling the amount of gloss or a mirror-like effect that you might have on your mesh in certain spots. There are many different ways of doing this, and different game engines do different things with this, but in Unity we have a specular mode and we have a metallic mode. So you have to choose between either one of those, and then you have smoothness as a second property, a second variable that you can also adjust to customize it even further. So this is all very dependent on artistic choice. I believe if you look at the Unity documentation, it literally says that it depends on artistic choice. It's not even so that if you have a metallic object that you need to use the metallic one. You can make a metallic object look good with the specular mode, and you can make a non-metallic object look good with the non-metallic mode. So, or the specular mode rather. So these are just options that you kind of want to mess around with and see where they go. And since this is a class for mostly people that are trying to get into programming in Unity, this is not something that you need to know that much in depth, because this is something that your 3D modeler will work on for you, and they'll provide you with maps that you just need to know how to implement. But to have some idea of what's going on here, this is what specular and metallic maps do, and smoothness goes with that as well. And you can have a separate smoothness map as well, or it could just be that your 3D modeler says set the smoothness to 0.5 and it'll look great. So a specular or metallic map will be more black and white. So if it's black, it will have a value of 0. If it has white, it's a value of 1. And the value is supposed to be clamped between 0 and 1. All right, now there's many of other maps that you can use as well on a 3D mesh, depending on who your 3D modeler is or what kind of object that they are modeling. And there are two more that I want to point out because you'll see them very often. One is ambient occlusion, which is a really cool one, because what ambient occlusion really does is it's calculating where soft shadows will occur from indirect and ambient lighting. And it's kind of depending on where you put the object in your scene. So an easy way to conceptualize this is what you see in this image. Just think about, like, this is going to put shadows in between your geometry, and it's going to add a little bit of extra detail without requiring an insane amount of processing power. It's going to require a bit, but it's a nice way to add some detail to your mesh by having all these little shadow areas left and right. The emissive map is a little bit easier to conceptualize, I would say. It really just points out where on your mesh you would like to have light emit from the mesh. And as you can see from this peculiar object here, it has some LED lights on it. And you can see in the part that is rendered with the emissive that it's only the LED parts that are actually shining, that are actually glowing, while the base of the construction is not. So this emissive map will probably have a value of 0 on the base and values of 1 wherever the LED is, or rather the areas of the UV map where you have the base are going to be black and these ones are going to be white. So anyways, different types of texture maps can do different outcomes. Now, how does your game engine know what to do with these maps and which maps it should use? Well, to figure that out, it uses materials. Materials are basically just files that contain information on how a specific surface of your mesh should be rendered. And usually that information will come with corresponding texture images, bitmap images like the albedos or the normal maps that are then plugged into the materials. And the shader and the game engine pretty much determine which information a certain material will need. If you're setting up your game engine to use specular maps, it's not going to be asking you for a metallic map, for instance. So that's what materials does, and as we are working on a project together, we'll use these plenty of times. And with that, we come to the last one, which are the shaders. So the shaders is basically the code that is going to take all that information from meshes, textures, and materials and turn that into 2D pixels on your screen, every specific color, so that you have a nicely rendered 2D scene based off of your 3D objects. And you can customize that code as well, depending on what rendering pipeline that you're using. But that's a topic that's a little bit too in-depth for this specific video. But we might get to there at a later time, or I'll provide some videos that you can look into for the further reading. Another side note here is that game engines are oftentimes using PBR these days. So PBR is physically based rendering, and it's a standard for your materials and textures where the materials want specific textures that are coded up in a way so that you are going to get really nice, accurate results. It's all about physically correct distribution of light and energy and consistent material definitions for your game to look as realistic as possible. It's mostly something about accuracy and standardization rather than performance, because it doesn't impact your performance of your game that much at all. So if you want to visualize everything that I just talked about, we can do that pretty easily with this diagram. So as you are putting your game together, you're going to have a scene. And in that scene, you're going to have a whole bunch of meshes. Every object in there, from your player character to, I don't know, if it's a first-person shooter, they might have a weapon, to maybe an item that you can pick up. They're all going to be meshes. Those meshes are going to have materials associated with them that will tell them which textures to use or which mathematical values to use for certain rendering techniques in certain spots of those objects. And even the way the object is placed in relation to each other, think about the ambient occlusion, will determine, will be information that will be helpful as well for then your shader and your game engine to turn into specific pixel colors that you see in this 2D space. So we start with a 3D scene, and then through code, which are actually our shaders, we get to 2D pixels. So okay, we've looked into culling. What are we going to draw from our scene? What is what are the objects that our code is actually going to take into account? Then we have looked at the various elements of how that scene is going to be translated into output. There's one more little thing that I want to point out, and that is post-processing. Because as you are doing this, as you generate this output, you could also mess around a little bit with it as well, with the pixel colors, as soon as you get that image. So post-processing is the idea that you're going to be using image processing to make changes to that rendered image in real time to get really cool graphical effects or make your image look better in some kind of a way. I'll show you some examples of that from a plugin that I've used in my own games. So this is the Blendables plugin for Unreal Engine. I used some of this, I think, with Bruckle, and it has a lot of options. For instance, the one that we are looking at right now allows us to do what they call a bleach bypass, which, as you can see, is changing the colors a lot. This one is adding bloom to the scene, which is lighting everything up or darkening everything up and creating very dramatic contrasts. And there's lots of different varieties in here. This is basically just a YouTube video. This one is colorizing everything to 256 colors. This is adding colors to it, taking colors away. This one does edge detection, so it actually allows you to just draw the outlines and just remove all color in between. And basically, the way you want to look at it is it's kind of like a Photoshop filter. For instance, this one here is doing Gaussian blur, so that is very similar to making an image blurry in Photoshop. The only difference here is that your engine is calculating this new image after you've already rendered everything that's in there. And you can use that for super cool effects that you might remember from games you've played, like night vision is a very common post-processing one. And the way that your game engine will take care of this is most of the time it's either you enable this, as you can see here with the mask. I mean, it puts your game into a spy mode without actually having to draw anything on screen for the player. But most of the time, what you will do is you will put an invisible cube or sphere somewhere in the map, and as soon as the player walks into it and the game detects that, you're going to start applying these Photoshop filters to the resulting rendering image. And that is basically what post-processing comes down to. For now, you just need to know what these things mean, because I'm sure they'll come up as we move along. I'll see you in another video. Bye-bye.